break next week, but the week after when we do the next one, it's not going to depend on any of this knowledge. So don't feel like you need to understand this to come to the next ones. But yeah, anyway, we'll see how it goes. We're sort of, yeah, I don't know. We'll see how it goes. So Harrison's going to start us off with a bit of high-level theory, like I said, and then I'll jump into the code. All right, Harrison, whenever you're ready.
I know, let's do this. Hopefully I don't sound too cooked, but if I do, apologies beforehand. All right, let's get started. All right. Okay, you work this time. Let me just get rid of all the random tabs I have. All right. So first things first, I'm gonna talk about two concepts. We're gonna be talking about memory. So obviously for memory, we have two different types of memory looking at the operating system's perspective. We have virtual memory and physical memory. So what's the difference between those two? In the past, we always use physical memory, which is usually a one-to-one mapping of your memory space to random access memory or other kinds of storage mediums. It should be noted that despite it being made of potentially many devices on several buses, the hardware usually virtualizes it to give us the impression of a continuous mapping, which is shown here. So in this case, we call it the main memory, but that's usually what we call physical memory, and it's continuous. It could be multiple sticks of RAM, or it could be some other sort of static memory as well. But these days, software programmers, we usually deal with idealistic abstraction. Usually it's called virtual memory, as shown here. So why are we doing this? Why do we have two different types of memory? Can't we just, put everything into main memory and just make it simpler? Well, the issue is because memory is a scarce resource. At any given instant, computers, there are actually thousands of processes running, each of them with their own address spaces and specific memory allocations. It will be in fact too expensive to put about a few hundred gigabytes of memory into the computer at any given time. And therefore, based upon how your CPU functions, usually you don't even need to use that much memory, because in reality, it only uses a subset, because processors only have several cores or several hardware threads. So therefore, we can only run several things at any given time. So therefore, we motivated a system which we need to have something called a virtual memory, which allows you to actually make things a lot simpler for the programmer. So in virtual memory, basically the whole idea is that it gives you a false impression that you have almost infinite amount of memory. So not infinite, but like quite a lot of memory compared to your actual memory, which could be like 60 gigabytes. So in that way, we could actually do a lot of magic with, modern processors. Well, I mean, so basically from this picture here, I hope you could see. Could you guys see the picture, or do I have to make it bigger?
We can see it.
Okay,
yeah, I can see it.
That's fine. So you can see here, if a memory isn't being mapped, it's actually being put into the disk. So yeah, it's quite interesting. Hold on, let me just get rid of this. Yeah. Where was I? Give me a second. So how do we actually do the mapping between virtual memory to main memory? Traditionally, it is the responsibility of a programmer to ensure whatever things you wrote fits into a CPU. It is still true for some niche CPUs and embedded systems where you have to physically map stuff into main memory, but in most modern CPUs or commercial CPUs, you have the virtual memory functionality to help you. So how this does is basically this hardware black box called the memory management unit, which does the mapping, and also it's also a software construct as well. Let me see. Yeah, and that's basically that. So how does the mapping work exactly? I have an example here. Okay. So in this example, we're gonna show you basically how paging works. If you've done computer systems, this is similar to what they teach, but we're gonna be focusing on the RISC-V specification, so how they advise you to do it. You don't have to follow it exactly, but this is usually what happens. So we're gonna start with a virtual page number or a virtual address. So that's VPN 0 concatenated VPN 1. So what this means is that we have a virtual address, and then we're gonna split it into 2 equal parts. The first part, it's gonna, so why do we split it into different parts? It's because we have 2 page tables in this example, in this specification. So basically what happens is that we have this thing called the SCTP register, which actually stores the root page table. Each page table contains a bunch of page table entries. And we'll explain what these are in detail later on, but I'm gonna assume you know what it is. And basically what's gonna happen is that we find the, basically we get this number here, which is a binary. We convert it into an integer. And we see, let's say we want to get the 5th entry from a page table. So we get that page table entry. From that page table entry, there's gonna be another pointer towards another page table. And from that page table, what we're gonna do is that we're gonna look at this number here, which is gonna point to another page table entry. And for that page table entry, we could actually determine the physical page number. Here's the algorithm in text, if you like reading. And so this is basically how we, in a high level, how we convert from a virtual page address to a physical page number. Any questions so far, or everything's good? Okay, we're good. And that's pretty much, yeah, pretty much virtual memory and physical memory in a nutshell. Now we're going to talk about something called privileges. There are 3 main types of privileges in RISC-V. There's the machine mode, which basically allows you full access to the physical memory, addresses, and hardware within and connected to, well, yeah. So basically gives access to the entire system. It is similar to this thing called a management engine on X86 or Intel processors. Search it up, it's actually quite interesting. And also system management mode and hypervisors, etc. So also have this thing called the supervisor mode, which is where you put the kernel. So basically your operating system actually lives in the supervisor mode. The machine mode denotes what memory regions the supervisor mode allows lives in, and basically tells it what instructions you could run and you could not run. And from that, the supervisor mode, you get the user space mode, which is basically where your applications live, and the operating system controls the user mode. If you Google what X86 Privilege Architecture looks like, you realize that the RISC-V privilege ring is actually significantly more elegant. This is also a main motivation why people actually want to move to something like RISC-V, because it's actually really, really lightweight and actually really simple to understand. From there, we're gonna show you how to actually do some memory manipulation in bare metal C. So assuming you could run a program, assuming you're in a bare metal RISC-V environment, you could just basically, what you could do, you could just basically choose a random memory location, and then basically you could just write to it. It's really simple, and basically you don't need to use malloc, anything like that. You just use the C runtime to actually denote, to write, you know, numbers into memory locations, which is quite neat. So you don't need to worry about segmentation faults, those kind of things as well, because those things don't exist at this level of abstraction. This is in machine mode, by the way. Here's a much neater, yeah, anyways, moving on. So now we'll talk about how to build a actually working system implementation. This is what Cody will partially do as well. So as we show here, we're going to organize all the virtual memory as pages, and also the physical memory as pages as well. There isn't really a motivation for why we organize physical memory as pages, but it's just neat that way. So this is this part is just the algorithm I showed all the way up here. And this is just like a high level overview of that. So I'm gonna assume you guys know what paging does, but we're gonna go through this slightly quickly as well. So we're gonna organize all the memory. So remember, memory is continuous, and we're gonna organize them into blocks of set sizes. In this case, let's call it, let's make it 4096 kilobytes. And we organize all these in linked lists. So page 0 links to page 1, which links to page 2, links to page n. So what we want to do is that we want to also record some metadata about each of the pages. So we need to record several things. That is, if it's being used, if it's not being used, and also if it's the last page within a set of allocations. Why would we want to record if it's last page in the set of allocations? Because that way, when we traverse down the pages, we could get specific blocks of memory, which maps to specific regions in the physical memory as well. How you set up the metadata is up to you. You could use a single byte array, or you could use bit manipulation. So it's really up to you how you want to get a metadata outlet, but it's a good thing to have when you're building a paging system. So after that, we're gonna talk about several, let's say, RISC-V data types. Well, actually, several registers and what they look like in reality. So if you remember from our example above, we have a physical address here and a virtual address and an SATP register. This is what actually goes into it, more or less. But this is how do I put it? This is like a different standard as well. Just keep in mind that this is SV39. The thing I showed you before is SV32. So the difference is that this is only 32 bits and this is 39 bits. Usually what happens is that because we're on a 64-bit computer, what we're gonna do is that we're gonna sign extend this to 64 bits when we're storing the data. Anyways, so let's go through what each of these means. Okay, so you have a page offset here. This is just universal between all standards. It's just a quirk. Don't worry about it too much. And VPN2, VPN1, VPN0 just denotes the page table entry, not page table levels. So root level, level 1, and level 2, which is the leaf level. Which actually points towards a physical page address. Excuse me. So a physical page address looks like this. So this part here is just the pointer, or basically address towards that memory location where the physical page starts, more or less. And this is the SATP register. Hold on. This is a page table entry, which actually has the page table addresses, which points towards the physical address or another entry, or another page table. These bits here, these are just for configurations, privilege levels, who has access to it, user, is it a global access memory location, etc., etc. So all these other bits here just for configuration, and these are here just for future standards. And this is what an SATP register looks like. So if you remember, this is the address which points towards the page table entry, which is stored in memory. Also, you have ASID and mode, which is not really relevant, but they're used for configurations and security reasons as well. So this is just a high-level overview of memory in RISC-V and difference between physical memory and virtual memory. I'm gonna pass it down to Cody to show you guys an actual example, and hopefully things will start making a lot more sense.
Cool. All right. I'll just share my screen then. All right. Hopefully you can all see my shitty draw-I-do diagram. Okay. So basically what we're going to do here is we're going to set up a really simple virtual memory example. Okay. So this is how we're going to set up main memory, okay? So we're going to have a bunch of code that we're going to run in machine mode. So remember, there are multiple different modes that the processor can run in, as Harrison described. We're going to be using machine mode and supervisor mode, okay? Machine mode has unrestricted access to the hardware. Supervisor mode has some restrictions. In particular, machine mode can enforce a virtual memory onto supervisor mode so that it has limited understanding of what the memory actually is. And that's what we're going to do today. We're going to force some memory restrictions on supervisor mode in machine mode. Okay. So yeah, so this is our memory setup. We have a bunch of code for our machine mode that's going to set everything up. And then we have a single page of memory set up for our supervisor mode. So in RISC-V, our pages are 4096 bytes or 1000 hex, okay? And so we're going to store all our supervisor mode code at this address, and we're going to basically, using the virtual memory or the memory management unit, we're going to map that address to itself, okay? So the supervisor, all right, well, when the process is in supervisor mode, it will see only this, okay? At this address, it will see its code, and then it will see everything up until this address, okay? Now, we're mapping an address directly to itself, okay? So, which may seem a bit redundant, but what it actually means is that the supervisor mode can't access anything outside this, okay? If it tries to load an address lower than this or an address higher than this, it will fail, and we'll see that in practice, okay? With this example, hopefully. Okay, so yeah, this is the kind of goal of what we're trying to set up, okay? And this is kind of how we're going to do it, okay? We need to set up, sorry, has someone unmuted themselves? Oh, Stuart.
Oh, it's me. Hi, sorry, I didn't realize it was
muted. No stress.
Hey, Stuart.
Okay, anyway, so in order to do this, we need to set up, or we need to program the memory management unit. Okay, so if we kind of try to understand how the memory management unit works a little bit, when it's enabled, okay, when it's running, all right, and I try to load or store to an address, okay, the memory management unit intercepts that load or store, and it basically breaks the address down like this, okay? So bits 11 to 12 are used as bits 0 to 11 are used as an offset within the page. And then these 9 sections of 9 bits are used to look through the page table to find where the actual memory is, okay? So here's the idea, okay? We want the supervisor mode, we want to map this address directly to this address, okay? And in doing so, we will map the whole page. So we'll get this address to this address, okay? And this address to this address, so yeah. So we'll start with that address, okay? If we break it down based on this diagram, we'll see that VPN2 is equal to OX2 or just 2, VPN1 is equal to 0, and VPN0 is equal to 10, okay? So now we need to set up the page table, okay? Each page table has 512 entries in it, okay? And 512 because 9 bits gives us 512 possible entries, okay? And so basically what we need to do is this, we have a sort of top level page table we start off with. And the page table is literally just an array, okay? It's an array of those 512 entries. And at address OX2, okay, we're gonna put a pointer to the next page table, okay? And so what the memory management unit will do is it'll pull this part out. It will look at our main page table, look at address entry OX2, and it will go to the next page table that is pointed to by that address, okay? And we'll just keep doing the same thing. So VPN1 is going to be OX0 for this address. So at that entry, which is entry 0, we're going to point to our final page table, okay? And then the final one is at entry 10, okay? Now entry 10 is not going to point to another table. It's actually going to point to the page in memory, okay? So it's going to point to that original address since we're doing an identity mapping, okay? So this is what we're going to try and do in code, okay? Yeah, okay, cool. Let me switch over to VS Code now. If I can remember how to use Zoom. Oh man, which one do I want? That'd be right. Yeah, this one. All right, so I've set up a couple of things, but for the most part, it's not super complicated. I got a linker script again. I mentioned these last week. I'm not going to go through them, okay? But this linker script is a little bit fancy. It does some cool stuff. It will lay out the memory as I described earlier. So if you remember, I said that the machine mode code is going to be at this address. The supervisor code is going to be at this address. So this linker script will make it so that that happens. Okay, I've got a basic assembly file, which we'll go through quickly, that just gets set up so that we can write some C code. I've got some C code that will set up the page table for us. For now, all I've got is a bunch of print functions in, okay? We don't have the C standard library, so I just wrote a bunch of print functions to make our life easier. All they do is print numbers and print character strings. It's nothing fancy. The actual setup page table function is currently empty. We're gonna fill that in. And then I have supervisor.c. So all of this code okay, will be put into that supervisor mode code section. All right, everything in this file will go in there. And again, I just got a bunch of print functions because we'll need those print functions in supervisor mode as well. So we'll need to have them there as well. And then we've got a main function, which currently just prints 2. So that, yeah, it doesn't really matter. Just a demo. Yeah, cool. And so if we jump back to our assembly, this is where we start. We have to start an assembly. All right. I've just done some really simple things. Oh, well, some semi-simple things. I don't want to spend too much time on the assembly, but basically this part is just disabling this feature that we don't need. If we don't disable it, it will get in our way. Okay. This part is calling the page table, the setup page table function. So we're just, as if you remember from last week, we're setting up a stack for it. We're setting up a return address, which is going to be here. And we're jumping to the setup page table function to execute it. Okay. This bit's a little bit more complicated. We're basically, this is how we get into supervisor mode. All right. So we're doing some slightly more complicated things to manipulate some of the registers so that we can get ready to go into supervisor mode. We have a separate stack, which will be inside this supervisor mode code block, because again, that is the only section of code that the supervisor will be able to access. And so, yeah, we've got a separate stack. We're calling the main function in supervisor.c. All right. And then, yeah, I'm not going to go through exactly how this works. It's a little bit weird. If anyone wants to ask at the end, I'd love to go through it, but I just don't have the time at the moment. So we'll skip over this and just assume this piece of assembly puts us into supervisor mode and runs main. Okay, cool. So to start with, I'm just going to do a super simple little sort of demo. We're just going to make a string that says hello. Very complicated, I know. And we're just going to print it. We're going to print, what we're going to do is actually, we're going to print the address. So we're just going to use this print number function I wrote, and we're going to cast the message address as a number. So we're just going to print the address of this string, okay, for reasons that will become clear later. Okay, we're just going to do some nice formatting as well, and then we'll print the actual string itself. Okay, and then yeah, we'll return. Okay, it's just complaining about, oh, I need to put base. Yeah. In supervisor mode, we're going to do the exact same thing. Okay. We're just going to print that message. It's going to complain because it doesn't know where that message is. So we just need to tell it that that message is in another file. Okay. And so, oh, I'm also just going to put a quick now in supervisor mode. Okay. Just so that we can keep track of what's happening. All right, I also have a makefile set up just because the compilation process for this is a little bit more complicated. I'm going to make all the code available on GitHub so you can go through that yourself. But for now, just assume it works, I guess. And if we run it, we'll see that our page table prints out the address where the message is stored and then the message itself. Then we get into supervisor mode, prints out the address that the message is stored and the message itself. Now, if we look at this address, okay, we'll see that this address is not in the supervisor mode range, okay? Not in its virtual memory address space, all right? Now, we haven't set up virtual memory yet, which is why it can still access this. But in theory, if we set up our virtual memory space properly, it should not be able to access this address. And so that's what we're going to try and work towards. We're basically going to get it to fail to print hello. So that's the goal. So yeah, let's get to that. Let's actually set up the page table, the juicy part, I guess. All right, let me just figure. Okay, so first we need some memory for the page table, okay? So each entry within the page table is a 64-bit integer, okay? We need 3 layers to our page table, so we're going to get 3 of them. Each layer has 512 entries, okay? So yeah, and that, if you are astute, you may actually notice that we have each 64-bit integer is 8 bytes, right? 8 times 512 is actually equal to 4096, which is our page size. So each page table actually takes up a single page. That's obviously intentional, but yeah, this 4096 is like our golden number. Memory is fully divided into regions of 4096 bytes, okay? And we need to keep everything aligned. Now, in keeping with that, we actually need to make sure this page table is aligned. So we need to make sure that the address of the page table is divisible by 4096, okay? It needs to line up with those sections of memory. And so we can do that with a special little GCC extension, oh shit, which is just this attribute aligned, okay? And this will just tell GCC to make sure that it aligns the start of this, all right, with it makes the start of this, or this page table start at an address that is divisible by 4096, okay? Yeah, cool. All right, so now we've got our 3 page tables, okay? We can move on to setting up that structure we saw earlier, okay? So our goal, okay, again, is to map this address, right, to itself in virtual memory space and nothing else, right? So we're just going to set up some variables, the address that we're kind of the virtual address, and where we want the virtual address to point to, which let's go, we'll just make it equal to address because we want it to point back to that. Okay. And this again is going to give us, it's going to give us the memory range from this address to this address. Oh, sorry, 3 Fs. Right. So it's going to give us 1 page of memory at this address. Okay. Now, how do we actually set up the page table? So again, when the MMU receives an address, it splits it up like this, okay? So bit 38 to 30 forms VPN2, okay? Which is going to be the first entry in the page table we need to set up, all right? So in the first page table, okay, at the address in this sort of section of the main address, sorry, it's hard to explain, but yeah, these 9 bits here are going to represent our entry into this page table, okay? And so to get them, we're going to just do some bit manipulation. So we're going to shift it back 30 bits, all right? And so this will basically just move these 9 bits to bit 0, right? So now we've got the number we wanted. And just to be sure that we only get 9 bits, okay? So this is 9 bits in total. We're just going to AND it with OX1FF, which is just 9 ones, all right? Those are just some bit manipulation techniques. They can be a bit confusing if you're not used to them, but they are very handy for this kind of stuff. Okay, so now what are we actually going to put in this page table? So remember, it's a uint64, so it's a 64-bit integer, all right? But what are we physically going to put there? All right, so the way that 64-bit integer needs to be arranged is like this, okay? So for the first few entries, the first 9 or 10 bits don't matter, okay? We don't have to worry about them. What is of interest is bits 53 to bit 10, which will be the address of the next page table, okay? And so in this case, the next page table is going to be page table 1, right? So we're going to get the address of page table 1. We will need to cast it to a uint64 so that C doesn't complain because it is technically a uint64. And one more thing, all right, we'll actually need to divide it by 4096, okay? Now, remember earlier I said all of these page tables need to be aligned to 4096, right? They need to be divisible by 4096. They're all a single page in size and they all need to be lined up on the page boundaries. That's so that we can fit it nicely into here, okay? We don't have enough space to fit the entire address. We sort of are missing the first 12 bits, and so dividing by 4096 gets rid of those first 12 bits. And they should all be 0 if the page table address is aligned anyway. That's just how that all works. So yeah, so we have now got the first, or the entry in our page table pointing to the next page table. We also just need to OR it with the number 1, okay? This will just set this valid bit to 1, okay? If it's 0, the page, like the MMU assumes that entry is invalid and not to be used. So we'll need to set all of the ones that we're using. We'll need to set the first bit to 1 just to tell it that it's valid. Okay. Now, the next page table is going to be almost identical to this one. We're just going to point to the last page table. So when we're going to page table 1, we want VPN 1 instead though. So we're going to get bits 21 to 29. So we'll shift it 21 bits to the right, and then we'll AND it with 9 ones, which will just give us VPN 1 on its own. And we're going to set it to point to the final page table. And yeah, it's also, we need to set it valid. Okay, so the last page table is the complicated one. Okay, we need to finally tell it where in memory we want this page to be mapped to. Okay, so again, we're now going to be using VPN 0, so we'll shift it to 12 bits, and again, it's at 9 bits, so we'll just AND it here to make sure we only get the 9 bits we're interested in. Okay, and now instead of pointing to a page table, okay, we're actually going to point it to this physical address that we've got. Okay, and we're still going to divide it by 4096. All right, this should be a page, so it should line up with the boundary, and it should be divisible by 4096. Okay, and yeah, that's kind of how this works. So we've got 3 layers of tables. Each table, we take part of the virtual memory address. We look up where the next table is in memory, and we just keep going down till we finally get to the physical address. Okay, and so this physical address could be another address. Okay, for now we're just doing an identity mapping, so we're mapping this address directly to itself, but it could be a different address. Okay, and we'll see that in a minute. I will show that after this first demo, but I just want to do a simple demo to start with. One other thing, we do need to start setting some of these as well. So in particular, this X flag, it means execute. So it means that this page of memory is executable by the processor. If this flag is not set and the processor tries to execute code within this page, it will fail and it will cause an error. Yeah, this W flag is right. Okay, again, if this flag's not set, you can't write memory to this page. And then this flag is read. So, you know, if this isn't set, you can't read from it. You can execute if you don't have read privilege, which is kind of a funny thing, but you can't do only write privilege. So you can't have a page that you can only write to and can't read from. That's not currently a thing. Yeah. But anyway, we'll just set those by, we'll just shift 1 to bit 3 and we'll OR it together. Again, these are a bit manipulation techniques. I can't go through them at the moment, but they'll basically just set bits 3 to 1 and 0 to 1. Okay, so it's executable, it's writable, it's readable, and it's a valid entry. Okay. Now, finally, we're going to return the page table address so that we can set the special register in memory. We'll return the page table address so that we can set up the registers that we need to set up in assembly. We need to do the last step in assembly. Okay. Now, the way the assembly register, which is called the SATP register, which is what we need to set in order to enable virtual memory, the way it's set up is it looks a bit like this. Okay. So bits 43 to 0 point to the top level page table, which is page table 0. Okay. Bits 59 to 44 are what's called the ASID. We're not going to worry about this. And bits 63 to 60 are the mode. Again, we're not going to worry too much about this. Basically, if it's 0, virtual memory is disabled. If it's 8, which is what we're going to use, virtual memory is enabled in the supervisor mode. That's kind of all we're going to look into that. Okay. So we'll need to do some bit stuff again just to get this to all pack into one 64-bit integer. So we'll take our top level page table 0, okay? And again, we will divide it by 4096. All the addresses in this are divided by 4096 because they all should be aligned to 4096. They should all be divisible by 4096. And then we'll set the mode. So we'll just need to cast 8 to a 64-bit integer. This is just kind of a quirk of C. If you don't do this, it will assume it's 32 bits. And then if you try and shift it 60 places to the left, that will be out of the range of the 32-bit number and you'll get a 0. So if we don't cast it like this, it will just give us a 0. So yeah, but yeah, that's just setting the mode to the number 8, all right, which again just enables supervisor mode. All right, So we've done all that. We've returned this thing that we want to write to the register. The last thing we do in assembly, okay, is we're just going to use this instruction, okay? This is the control status register write instruction, okay? And so it's writing to this special register, the setup register, which is a control status register, which controls memory, virtual memory. We're going to write A0, which if you remember from last week, C will store the return value in the register A0. So after we call this function, A0 should have the return address, the return value stored in there, which is this special number that we've set up to be put into this register. All right, so hopefully you followed along with all of that. We should now have virtual memory. So just to remind you what happened when we didn't, I'll just make it again quickly and we'll run it. And you see that in machine mode, we had no problem printing the string, okay? And then even when we got into supervisor mode, we had no problem printing the string, even though this address is not in the supervisor mode code's virtual memory space, right? Because we hadn't enabled virtual memory yet. So now with one register right, we are going to enable virtual memory. We make it and hopefully, something goes wrong. All right, hold on. Just give me 2 seconds, guys. I just need to figure out what went wrong. Never works the first time, does it?
Yeah, it's like that sometimes when you're doing a demo in front of a bunch of seniors and suddenly your
breaks.
Demonstration breaks. That happened to me a few times. That was fun.
Yeah. God damn it. What have I done? 3. Oh, yes. No, I did. I know what I did. I did this last time as well. Sorry. Okay. So one little other final thing we have to put in here. This is an extra page table entry. I'm not going to talk too much about. Basically, it just maps in this address. If you remember last week, to print, we stored numbers at this address. Okay. We're just going to map that in so that the supervisor can actually print. Okay. Don't worry too much. This is kind of a hack. It actually allocates like an entire gigabyte's worth of memory for the thing. It doesn't need anywhere near that much, but it won't interfere with the rest of what we're doing. Okay. But yeah, it just to let us print. So just, you can pretend it's not there. Honestly, it doesn't have an impact on what we're doing. Okay. Now, if we run, it still doesn't work. Damn it. I was really hoping that would work.
Use the backup code if you have it.
I do, but it's a bit of a mess. What have I done? 1096, shift 60 spaces, 0, h2 equals 0, 6, or valid 1096. Oh, you know what I've done? Hold on, sorry. This address, sorry, I've completely forgot. Okay. So this address here, right, it actually starts at bit 10. So we just need to shift it 10 spaces. Sorry, this is all that crap. Fuck, what have I done? Okay. We just need to shift it 10 spaces. Okay, so the address occupies the space from bit 53 to bit 10. Okay, so in order to make it start at 10, we're just going to shift it 10 spaces for this. Sorry, I completely forgot about that step. And I'll just update all of these to do that. And then this physical address needs to be shifted 10 bits as well. Yeah, cool. All right. Now it will definitely work. Yes. Okay, cool. So we can see we had no problems printing in machine mode. We got into supervisor mode. And then when we tried to print this address, okay, again, it was not in this range here. So it just failed. And what it did was it would trigger the processor error handling system, but we haven't set that up. So it just sort of does nothing. Okay. Again, all we have to do is disable that. All right. And if we make again, run again, has no problems. All right. But if we enable it, make, run, and it can't load that address because it's not mapped in. Okay, cool. All right. So that's all well and good, but I want to show another example, okay? To show this, we're going to keep most of the same code, so hopefully this shouldn't take too long. But we're gonna now put a string in the supervisor mode code, okay? So I just have this tiny little string set up, okay? It's just all underscores, all right? And now this is in the supervisor mode file, so it will be in the supervisor mode code section of memory, all right? So supervisor mode should have no problems accessing it. We'll just print it out as well. We'll get rid of printing this and we'll print the, oh, sorry, this is the wrong one. Yeah, I'm just gonna copy these ones to make life a little bit quicker. We're just gonna print that out, okay? And we'll also print it out in the page table setup, okay? So instead of printing the previous message, we'll get rid of it. We're just gonna tell, the page table code about this message. We're gonna tell it it's defined in an external file. And we'll just get the page table code to write a little string to it. So currently it's all underscores, okay? We'll just get the page table to write. I'm doing a really hacky write where I write each individual character. So we're just gonna write hi with an exclamation mark. And again, similar to in supervisor mode, we're just gonna print out what that string is. And we're also printing out the address it's stored again, just so that we can compare. Okay, so nothing too fancy. We'll we have the, yeah. So now that the string is in the supervisor mode code, both can print it out because again, machine mode has unrestricted access and supervisor mode can access anything within this address range, okay? So now that it's stored within a spot that the supervisor mode can access in its virtual memory, it can get the string. Cool. Now, what if we do something really trippy? What if we move this block, okay, to 80 million and 20,000 instead of 80 million and 10,000, okay? But we're still gonna make supervisor mode think it's here, okay? So but when it's stored in physical memory, it's gonna be at a different address, all right? So in our page table, okay, instead of mapping this virtual address to the same physical address, we're going to map it to a different physical address, okay? And because we set up our code properly, this should pretty much all work straight out of the box. The only other thing I got to do is tell the linker to load the code at a different spot. So I'm just going to tell the linker to make the code think it's here, but it's actually going to be loaded here, okay? And yeah, that's pretty much all there is to it. So if we make, the link is going to complain now because we're doing some dodgy shit, but don't worry about it. And we run, we'll see that even though the machine mode is reading this address, so it's stored the hi at this address, okay, and it printed it out, no problems. When the supervisor code gets there, it's not seeing that string because it's now at a different physical location to where the machine code thinks it is, okay? So it's in a completely different location. But it thinks it's here, right? And so it's telling us there's nothing there, but the machine mode code, which has unrestricted access, knows that there is actually something there, okay? And just to sort of show finally, we can also, in the machine mode code, so we've just offset it by a pretty straightforward number. So it's pretty easy just to, what was I gonna say? We'll just set up the address to, we'll just add this much to the address. So we're just going to offset it to the actual address where the supervisor mode code is stored. And we're going to do pretty much the exact same thing. We're just going to copy a string and print it over. We're going to copy the string ha instead of hi though, just so that we can see the difference. Okay. And now when we run the code, or when we make, and when we run, we'll see that the machine code, the machine mode has stored two strings. It's stored hi at this address and it's stored hut at this address. But when it's in supervisor mode, it thinks it's at this address, but it's actually reading the string stored at this address. Okay. And so, yeah, that's kind of a bit of a demo. Hopefully you guys sort of followed along and got the idea of what was happening. That's pretty much it though. Were there any final questions? Maybe we'll stop the recording now for the...
Roger, Roger.